My issue with light is that it just doesn't seem to want to knuckle down and be anything in particular. It refuses to be just a wave and propagate nicely through space, interfering with itself because it demands to carry momentum, and also it wishes to scatter off of itself, something that most waves agree nicely not to do. So it becomes a very difficult phenomenon to understand because it has a lot of bitty parts that don't necessarily seem to fit nicely together. Today what I want to talk about is what should be a nice simple phenomenon. The idea that light has a polarization. You're probably reasonably familiar with the idea of a polarization, or at least linear polarization, but if you're not, you can imagine that, say you were driving down the highway, freeway, road, motorway, and you're listening to a song you like on the radio and you're sort of bobbing your head along with it. You can imagine that if you trace the path of your head nicely bobbing through space along the road, then a sort of wave-like pattern would emerge. And as your head is only bobbing up and down, you can say the polarization of that wave is up and down also. And you're probably reasonably familiar with the idea of a polarizer, which is basically a device which selects polarizations and only allows certain ones through. A common example of a polarizer which you've probably seen is something like your sunglasses, which are good at reducing glare off of road surfaces because they effectively cut out just one polarization of light. So if you look at a linearly polarized light source through a polarizer, then at one orientation of the polarizer, light should happily make its way through to you, but if you turn the polarizer 90 degrees, you shouldn't see any light. And to understand sort of how a polarizer works, you can think back to that idea of an electric field oscillating up and down through space. A polarizer is just designed in such a way that the electrons within it are very eager to start oscillating in a certain direction. So if the electric field happens to line up with that direction, then the light in it is absorbed, sort of similar to how you might imagine a radio wave being absorbed by an antenna. However, it wouldn't be light if there wasn't a certain problem with this model, a certain limitation which hits you in the face when you actually try and go to do an experiment about it. So the experiment that we're going to do is pass a laser beam through a linear polarizer. So all that should mean is that the laser beam we put in should come out polarized in one direction, oscillating effectively up and down. And just as we saw before, what we're going to do next is place a second polarizer at 90 degrees to the first. What do we expect to happen? We expect no light to get through. And so we can happily rotate this second polarizer back and forth a few times to show that yes, in fact, when the polarization is aligned with the incoming polarization, it lets light through. When it's not aligned with the incoming polarization, then it doesn't let any light through. But I say again, it wouldn't be light if it actually wanted to follow such a simple set of rules. What happens if we put another polarizer between these two polarizers? Take a second to think for yourself, what does it make sense would actually happen in this case? Surely any linearly polarized light would be at least partly obscured by the second polarizer, regardless of what angle it's at. But still beyond that next polarizer, we should see no light. Because after all, they are turned at 90 degrees to each other, so no light should be getting through. However, if we put the second polarizer in, what do we see? We see light is more than happy to come through. Damn it. Okay, so it's reasonably obvious that somewhere along the line we made a false assumption. Where was that actual false assumption? Where did it come into play? The fault in our line of reasoning has come from the idea that we assumed that linearly polarized light had only this one component to it oscillating up and down. And although we proved that concept to ourselves by using a polarizer and saying that at 90 degrees no light got through, we didn't actually accurately describe the true nature of light, we only described how it was manifesting in this situation. What we must have instead is that light must have two polarization components orthogonal to each other, the average of which add up to the polarization state. If we think about polarized light this way, this is what allows us to make sense of this whole picture. It allows us to propagate light through that first polarizer. It becomes linearly polarized overall, but still has those two orthogonal components. As this polarized light hits the second component, one of those polarization components is removed, but the second one remains and is allowed to propagate through. This linearly polarized light must also have two orthogonal components. So upon striking the final polarizer, only one is removed and the other is allowed through. And this is what allows us to get some amount of light. However, as is always the case with light, there is one final component to the problem, and that comes from the idea that light is made up of discrete particles of energy called photons. We said that light propagates through this system, and as it gets to the middle polarizer, one component of that polarization is absorbed and the other is allowed to pass through. However, if we lost any energy in that process, then you'd expect a different coloured photon to come out. and it doesn't. Red comes in, red goes out. And to explain this, we are forced to resort to the only robust tool set we have left in which anything is possible as long as the amplitude is small enough: quantum mechanics. How do we resolve this dilemma? We are forced to say that quantum mechanics is a probabilistic process. At each step along the way, there is a probability that the photon will be absorbed or that it will get through. Which does, I admit, sound like at some stage a physicist has just held up the white flag and admitted defeat, but this is the state of the universe. And who are we to argue?